Dear students, today I am going to discuss group theory. I will emphasize on the counting techniques in group theory, which will help you a lot to solve the problems in competitive exams. Let us start. First of all, we will discuss some tools, mathematical tools, which will help you to solve the problems. The first one is Euler's phi function. What is the definition? The number of positive integers less than n, which are co-prime to n, denoted by phi n, is called Euler's phi function. So what is phi n? Is equal to cardinality of the set of natural numbers m such that m less than equal to n and greatest common divisor of m and n is equal to 1. Now we have some results. Number one, if p is a prime number, then phi p is equal to p minus 1. Second one is, if p is a prime, k greater than 0, then phi of p raised to power k is equal to p raised to power k minus p raised to power k minus 1 is equal to p raised to power k into 1 minus 1 by p. The third one is, if n greater than 1 has prime factorization, n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2, p3 raised to power alpha 3 up to pk raised to power alpha k, then phi n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2, p3 raised to power alpha 3 up to pk raised to power alpha k into 1 minus 1 by p1 into 1 minus 1 by p2 up to 1 minus 1 by pk. So these are some results which will be very helpful to us. Now, next tool is number of divisors, that is denoted by tau n. Given a positive integer n, let tau n denotes the number of positive divisors of n. Now we have a result based to calculate tau n. If n greater than 1 has prime factorization, n is equal to p1 raised to alpha 1, p2 raised to alpha 2, p3 raised to alpha 3 up to pk raised to alpha k, then tau n is calculated as, we will add 1 in the powers. So tau n is equal to alpha 1 plus 1, alpha 2 plus 1 up to alpha k plus 1. Now, next tool is sum of divisors, that is denoted by sigma n. Given a positive integer n, let sigma n denotes the sum of positive divisors of n. What is group? A group is a set G with a binary operation G cross G to G, defined by this ordered pair G comma G prime goes to G star G prime, satisfying the following properties. The first one is existence of identity element denoted by E, which satisfies the following property: G star E is equal to E star G is equal to G. The second property is existence of inverse, means every element G of G has an inverse denoted by G inverse, which satisfies the following property: G star G inverse is equal to G inverse star G is equal to identity. The third property is this binary operation star is associative, means G1 star G2 star G3 is equal to G1 star G2 star G3 for all G1, G2, G3 belongs to G. Now we have some examples. Set of integers denoted by Z, set of rational numbers denoted by Q, set of real numbers denoted by R, set of complex numbers denoted by C. These all sets with respect to addition are groups. Set of integers with respect to multiplication is not a group. Why not a group? Because here multiplicative inverse does not exist. Next example is set of rational numbers with respect to multiplication is not a group. Why not a group? Because 0 don't have multiplicative inverse here. Next example is the set Zn is equal to 0, 1, 2, 3 up to n minus 1 for n greater than equal to 1 is a group under addition modulo n. For any j greater than 0 in Zn, the inverse of j is n minus j. This group is usually referred to as the group of integers modulo n. Now, what is abelian group? A group G is said to be abelian or commutative if A star B is equal to B star A for all AB belongs to G. Now we have some examples. Set of integers, set of rational numbers, set of real numbers with respect to addition are abelian groups. Second example is set of n cross n matrices with entries from the field R with respect to addition forms a abelian group. But set of n cross n non-similar matrices with real entries denoted as GL and R forms a non-abelian group under matrix multiplication. This group is known as general linear group of degree n. Next example is Sn for n greater than equal to 3 is non-abelian group. This Sn is known as symmetric group of degree n. Let us discuss this group. First of all, we will discuss what is permutation. Let S be a non-empty set, then any mapping F from S to S, which is on1 and on2, is called a permutation on the set S. In other words, permutation is a bijective mapping from set S to itself. Let us define some examples. Let S is equal to 1, 2, 3. A map F from S to S defined as Fi is equal to I for all I1, 2, 3. So this is an identity mapping. Second example is a map G from S to S defined as G1 is equal to 2, G2 is equal to 3, G3 is equal to 1 is a permutation on set S. Similarly, we can define H from S to S defined by H1 is equal to 1, H2 is equal to 3, H3 is equal to 2 is a permutation on the set S. Similarly, we can define other permutations also. So now we want to see how many permutations are possible on set S. So we have a remark. Let S be a non-empty finite set with cardinality n. The number of 1, 1 onto mappings from S to S is equal to factorial n. It means we can define factorial n number of permutations on set S. Now, composition of permutations. If F and G are two permutations on a non-empty set S, then composition of permutations, that is F circle G and G circle F, are also permutations on set S, because composition of two bijections is again a bijection. But in general, we cannot say that F circle G is equal to G circle F. These may or may not be equal. Let us see example. Let S is equal to 1, 2, 3 and consider two permutations on set S defined as follows. F from S to S such that F of 1 is equal to 2, F of 2 is equal to 3, F of 3 is equal to 1, and G from S to S such that G of 1 is equal to 1, G of 2 is equal to 3, G of 3 is equal to 2. Then F circle G and G circle F, we clearly, easily we can calculate. Here we have calculated, you can see easily. So what is the conclusion? F circle G is not equal to G circle F. So we can say from here that permutations need not commute. So symmetric group is non-abelian. Now explicitly we are defining what is symmetric group. Let S is equal to 1, 2, 3 up to n be a finite set. Then Sn is the collection of the mappings from S to S which are 1, 1 and on 2. This set Sn forms a group under the composition of mappings. This group is called symmetric group, and cardinality of this group Sn is equal to factorial n. Now we have a notation. Suppose we have a symmetric group S5. Let us take one element sigma from S5. Let sigma is equal to in matrix form. Generally, we use this notation to denote the permutation. The first row elements denotes the elements of domain. Second row elements are images of the corresponding elements in first row. So we can write another notation. Cycle decomposition of sigma is equal to, we can write in cycle form 1, 2, 3, 4, 5. What is the length of this cycle? Length is 5. So this sigma is called 5 cycle. Let us take another example. Tau is equal to 1, 2, 3, 4, 5. And images are 1, 2, 4, 3, 5. We can write this permutation as 1, 2, and 2 cycle 3, 4, and 1 cycle 5. We can multiply these cycles, so we will get the answer 3, 4. So this is a 2 cycle. Now transposition. What is transposition? A 2 cycle is called a transposition. What is even permutation? Let sigma belongs to Sn. We say sigma is an even permutation if the number of transpositions required to express sigma as a product is how many? Even. Odd permutation. Let sigma belongs to Sn. We say sigma is an odd permutation if the number of transpositions required to express sigma as a product is odd. Next result is order of a k cycle is k. Another result, every element sigma belongs to Sn can be written as a cycle or as a product of disjoint cycles. Now, what is alternating group? Let Sn n greater than 1 be a symmetric group, then An is defined as the elements of Sn which are even permutations. So this An is forms a group of order factorial n upon 2. This An is called the alternating group. Moreover, we can say An is a subgroup of Sn. Now we have a counting technique. The number of distinct cycles of length k in Sn is equal to factorial n upon k into factorial n minus k. Let us take one example based on this result. The number of distinct cycles of length 4 in S5 is equal to, we can calculate easily. So answer will be 30. Now, what is order of an element of a group G? If G be a group, then order of an element A belongs to G is the least positive integer R such that A raised to power R is equal to identity, where E is the identity of element of G. If no such least positive integer exists for an element A belongs to G, then we can say that A has an infinite order. We use the notation OA to denote order of an element A. Now we have some results. If A belongs to G, then order of A is equal to 1 if and only if A is equal to identity. What does it mean? It means identity element is the only element of the group which has order 1. Now second result is if G is a finite group and A belongs to G, then order of A can never exceed the order of G. What is next result? If sigma belongs to Sn, has cycle decomposition, sigma is equal to sigma 1, sigma 2, sigma 3 up to sigma k, and sigma is a mi cycle and these cycles are disjoint, then order of sigma is equal to LCM of m1, m2, m3 up to mk. Here note one point that this disjointness of cycles is very, very important. If cycles are not disjoint, is sigma, let us discuss again. Example, sigma is equal to 1 2 into 1 2 3 is equal to 1 into 2 3 is equal to 2 3. So sigma is a 2 cycle. It is also a product of 2 cycle and 3 cycle. But order of sigma is equal to 2 because after calculation it is a 2 cycle. But initially what we have, sigma is equal to multiply of 1 2 and 1 2 3, two cycles, one cycle of length 2 and another cycle of length 3. So what is LCM? 6. But one point is to be noticed that these cycles are not disjoint because 1 is the common element in both the cycles 1 2 and 1 2 3. So we cannot apply above result in this example. Now, what is subgroup? Subgroup, let G be a group. A subgroup H of G is a subset of G which has the following properties. Number 1, H is closed under the binary operation of G. Means AB belongs to H implies AB belongs to H. Second property is identity element E belongs to H. Third property is if A belongs to H, then A inverse belongs to H. We have a counting technique. Number of subgroups of Zn is tau n. So we have a one problem based on the result. Find number of subgroups of a cyclic group Z6. Answer is number of subgroups of a cyclic group Z6 is tau 6. And we know how to calculate. First of all, we will write prime factorization of 6, that is 2 raised to power 1 into 3 raised to power 1. And how to calculate tau? We will add 1 in the powers and multiply. So 1 plus 1 into 1 plus 1 is equal to 2. Now, what is cyclic group? Let G be a group and let A belongs to G. The subgroup generated by A is the subgroup A raised to power n belongs to Z, is denoted as generated by A. Here A is called the generator of the group. We have some results. If D is a positive divisor of n, the number of elements of order D in a cyclic group of order n is phi D. Number 2 is let G be a group of finite order, then G is a cyclic group if and only if G has at least one element whose order equals to the order of the group. Number 3 is every cyclic group is abelian. Number 4, number of generators of a cyclic group G of order n is phi n. One example based on this result, number of generators of a cyclic group of order 27 is phi of 27, that is phi of 3 raised to power 3 is equal to 3 raised to power 3 minus 3 raised to power 3 minus 1 is equal to 27 minus 9, that is 18. Next result is every group of prime order is cyclic. Very important result. Number 6 result, the number of subgroups of a cyclic group of 12 is tau 12. Here we can take any number in place of 12. I have taken one example, 12. And tau 12 is equal to tau 2 raised to power 2 into 3 raised to power 1 is equal to, we will add 1 in the powers and we will do multiplication. So answer will be 6. Now we have a question. Is abelian group cyclic? Answer is no. We can give one example, and that is Klein 4 group of order 4. The one element is identity element, that is of order 1, and 3 elements A1, A2, A3 are of order 2, which satisfies certain properties. Now question is this Klein 4 group is cyclic? Answer is no. Why it is not cyclic? It is not cyclic because it has no element of order 4. Here we have used the result number 2. This result number 2 we have used in this example. Now you can say, sir, you have given a abstract structure of Klein 4 group. Can you give some example? Yes. Let us take G. The collection of these 4 matrices is a Klein 4 group. Clearly you can check. Here one element is of order 2 and 3 elements are of order 2. So this is a Klein 4 group. Now we have some definition and some results. Center of a group denoted by ZG is equal to A belongs to G, such that AX is equal to XA for all X in G. If G is a abelian group, then ZG will be the whole group G. So ZG is equal to G, if and only if G is abelian. Now, center of G is a subgroup of G. We have a result. If cardinality of G is equal to P raised to power n, where P is a prime, then cardinality of ZG is greater than 1. What is homomorphism? Suppose we have two groups G and G prime. A homomorphism of groups is a function phi from G to G prime such that phi of AB is equal to phi of A into phi of B for all AB belongs to G. Means, suppose we have two elements and we will multiply, then product of image of the product is equal to product of the images. Now we have example. Phi from Z to Z, fix an integer n. Phi of A is equal to Na, which can be written as A plus A up to A, is a homomorphism. Here Z is a group with respect to addition, because we know Z is not a group with respect to multiplication. So clearly we can check this property, phi of A plus B is equal to phi A plus phi B. So this phi is a homomorphism from Z to Z. Now we have a counting technique. The number of group homomorphisms from Zm to Zn is greatest common divisor of M and N. We have example based on this result. The number of group homomorphisms from Z2 to Z3 is GCD of 2, 3, that is 1. Now, what are isomorphic groups? Two groups G and G prime are isomorphic groups, or we can say that they are isomorphic to each other if there is at least one mapping G to G prime, which is isomorphism. That is homomorphism 1, 1 and on 2. Now we have examples. Z4 and K4 are not isomorphic. Why not isomorphic? Because Z4 is cyclic group and K4 is not cyclic group. Second example, S3 and Z6 are not isomorphic. although both have order 6, but not isomorphic because S3 is non-abelian and Z6 is abelian. Next example, any infinite cyclic group is isomorphic to Z. Next one is any finite cyclic group of order n is isomorphic to Zn. Now we have a result. Let G be an abelian group of order n is equal to P1 raised to power alpha 1, P2 raised to power alpha 2, P3 raised to power alpha 3 up to Pk raised to power alpha k prime factorization of n. The number of abelian group of order n up to isomorphism is equal to P alpha 1, P alpha 2, P alpha 3, P alpha k, where P alpha is denote the number of partitions of alpha I. The number of non-isomorphic abelian groups of order 2 raised to power 2, 3 raised to power 3, P raised to power 4 is equal to P2 into P3 into P4. And clearly we can see that partitions of 2 are 2, partitions of 3 are 3, partitions of 4 are 5. So answer will be 30. Suppose we have a homomorphism phi from G to G prime such that phi of AB is equal to phi A into phi B for all AB belongs to G. Kernel of phi is equal to A belongs to G, phi of A is equal to identity of G dash, image of phi of A such that A belongs to G. Clearly we can see that kernel phi is a subgroup of G and image of phi is a subgroup of G prime. Now what is normal subgroup? Let G be a group. A normal subgroup H of G is a subgroup satisfying given G belongs to G and H belongs to H, G inverse belongs to H. Kernel phi and ZG are normal subgroups. Cosets. What is cosets? If H is a subgroup of a group G, the left cosets of H are subsets AH, A belongs to G, right cosets of H are subsets HA, A belongs to G. Now, what is the index of subgroup? The number of left cosets of H in G is called the index of H in G, that is denoted by this symbol. So now we have a Lagrange theorem. Let G be a finite group and H be its subgroup of G, then the order of H divides the order of G. What is Cauchy's theorem? Let G be a finite abelian group. Suppose that a prime number P divides the order of G, then G has an element of order P. Result. Suppose G has order P or P square, where P is a prime number, then G is abelian. One example based on this result, a group of order 9 that can be written as 3 raised to power 2 is abelian. Now, Syloh's theorem, very important theorem. First of all, we will discuss Syloh P subgroup. Let G be a finite group. Let P be a prime number. Say cardinality of G is equal to n. Cardinality of G is equal to n can be written as P raised to power E into M, where E greater than equal to M, P greater than equal to 1, and P and M are co-prime. What does it mean? It means P does not divide M. Then Syloh P subgroup of G is a subgroup of order P raised to power E. First Syloh theorem, what it says, let G be a finite group of order n, let P be a prime number such that P divides n. We can write cardinality of G is equal to n is equal to P raised to power E into M, where E greater than 0 and P does not divide M, then G has a Syloh P subgroup. Syloh's second theorem, what it says, let G be a finite group and let P be a prime that divides cardinality of G, then any two Syloh P subgroups are conjugate. What does it mean, conjugates? We say that two subgroups are conjugate if H is equal to G K G inverse for some G in G. Third Syloh theorem, what it says, let G be a finite group and P be a prime number that divides cardinality of G. We can write cardinality of G is equal to n is equal to P raised to power E into M, where P does not divide M. Let S be the number of Syloh P subgroups of G. Then S, here this S is small case letter. S divides M, and second property is S is equal to AP plus 1 for some A greater than equal to 0. Sorry. Now we have an example. Let G equal to S3, cardinality of G is equal to 6 is equal to 2 into 3. S2 is equal to the number of Syloh 2 subgroups. S3 is equal to the number of Syloh 3 subgroups. Third Syloh theorem implies S2 divides 3 and S2 is equal to 1 plus 2A. So S2 is equal to 1 or 3. Again, third Syloh theorem implies S3 divides 2 and S3 is equal to 1 plus 3A. What is the possibility of S3? So only one possibility is there, that is 1. So S3 is equal to 1. If G is equal to S3, means symmetric group of degree 3 is equal to, we know the structure, then S2 is equal to 3. If G equal to Z6, then S2 is equal to 1. Now we have a result. Let P and Q be primes and P less than Q. Let G be a group of order P into Q. Then G has a normal subgroup of order Q. By using above result, we can say that a group of order 6 that can be written as 2 into 3. 3 is bigger. So this group of order 6 has a normal subgroup of order 3. So we have some references. First one is NPTEL course Introduction to Abstract Group Theory by Professor Krishna Hanumanthu, a renowned mathematician in India. Second one is Contemporary Abstract Algebra book by Joseph A. Gallian. Third one is Modern Algebra book by A.P. Singh. This is a actually all these references are very important, but for counting techniques, third one is most important. This is a very important book for competitive exams, which can help you a lot. So happy learning. Thank you so much. Thank you so much again.